Welcome back to Logic, Language and Information. In this lesson, we'll get some experience putting PROLOG to use, working on a project to solve Sudoku puzzles. This lesson is a tutorial or workshop rather than a lecture, and there's in fact no new content. So in that sense, it's sort of optional inside the series of lectures. So for those of you staying around, let's begin. From last time, we know how to write program clauses and a logic program in PROLOG notation, and how to ask PROLOG whether or not a goal is a logical consequence of a logic program. Our project is to solve 4x4 toy-sized Sudoku puzzles. Now, most people will have seen the usual 9x9 Sudoku puzzles at some point. They've become quite popular for the last 10 years or so. Sudoku puzzles are solved by logic alone, so that makes them a good choice for automated reasoning. We're going to work with toy-sized 4x4 puzzles because they are extremely easy to solve, so the logic is quite transparent, yet they contain all the same structure as the regular-sized puzzles. As we'll see in this lesson, even little 4x4 Sudokus end up generating quite enough work and require a large number of propositional program clauses. In our 4x4 grid, we can label the cells with capital letters, A, B, C, and so on up to P. Any 16 names will do. The cells are naturally arranged in 4 rows, 4 columns, and 4 blocks, as shown. A correctly completed 4x4 Sudoku puzzle must contain a permutation of the numbers 1, 2, 3, and 4 in each of its rows, each of its columns, and each of its blocks. That is, all 4 numbers without repetition in each row, column and block. To make sure we have puzzles with unique solutions, we will assume that each puzzle has an initial assignment of the numbers 1, 2, 3 and 4 with no repeats to 4 pairwise independent cells in the grid. This will be made precise in a bit. Immediately, looking at this particular puzzle, we can see that cell D must contain the value 3 because there is a 1 in the same row, a 2 in the same block, and a 4 in the same column. Likewise, the correct values for the cells E, J, and O are immediate consequences of the initial values shown in red. It is precisely these reasoning steps that we want to explicate in our logic program in order to capture the process of solving such a puzzle. Our project is as follows. We want to represent basic propositions like cell D has value 3 or cell B has value 1 as atomic formulas, and then represent as much as we reasonably can of the structure of the problem in a program clauses in a propositional PROLOG program in order to solve these puzzles using PROLOG queries. The bulk of the work for the project is the problem representation. First, the atomic formulas. There will be 64 of them. For each of the 16 named cells, there are 4 possible values they may take. We have to start with the atom names with a lowercase letter, so let them all start with V for value. In Sudoku example 1, we start with the facts. Value of B is 1, value of G is 2, value of L is 4, and value of M is 3. Intuitively, the cells B, G, L, and M are pairwise independent because any 2 of them are in different rows, different columns, and different blocks. We'll now make this more precise. We will say 2 cells are Sudoku related exactly when they are different, but either in the same row, the same column, or the same block. The Sudoku relationship is symmetric. It is a simple matter of counting to establish that each of the 16 cells have 7 other cells that are Sudoku related to them. Conversely, we will call 2 cells independent if they are not Sudoku related to each other and different. Then a set of cells is pairwise independent when any 2 different cells in the set are independent of each other. Visually, it is easy for us to see all the cells Sudoku related to a given cell. We only scan the Sudoku related cells when solving the value of a given cell. For access by a computer, we could store the Sudoku relationship data as a list of lists or as a table with an entry 1 when a pair of cells are Sudoku related and an entry 0 when they are not. Working as we are in propositional logic, we could go ahead and add a further 112, which is 16 times 7, more atomic propositions, say of the form SXY, expressing that cell X is Sudoku related to cell Y. However, pragmatically, we will not take that path simply because the original 64 atoms expressing cell values are already quite enough to deal with. In the successor course, Logic, Language and Information 2, we're going to extend beyond propositional logic to predicate logic, within which we can directly express this sort of relationship data as atomic formulas of the logic. In predicate logic, tables like these are key ingredients in giving the semantics of the language. In the logic programming application section of LLI 2, we will revisit this Sudoku project and see how much easier it becomes in a richer language and logic. But back here, working in propositional logic, we will just make do without having atoms in the language to describe the Sudoku relationship. So we develop a revised or refined statement of the project as follows. Our task is to design an algorithm that takes as input a 4x4 Sudoku puzzle with approved initial state and produces as output a propositional PROLOG program which will solve just that puzzle using program clauses containing only the 64 cell value atoms. We will describe an algorithm and how to implement it by hand. To fully automate the process, the algorithm could be implemented in the richer predicate PROLOG with extensions for writing to files or implemented in a different programming language. At stage 1 of the algorithm, let theta 1 be the set of 4 cells initially valued in the given puzzle. And let sigma 1 be the set of 12 remaining cells yet to be valued. For each of the cells X in sigma 1, the unvalued, we will search for 3 cells, Y1, Y2 and Y3 in theta 1 with 3 distinct values, J1, J2 and J3 respectively, with all 3 of these cells Sudoku related to X. Then we'll write down the PROLOG program clause, value of X is I if, :, value of Y1 is J1, comma, value of Y2 is J2, comma, value of Y3 is J3, full stop. Here, I is the value from the set 1, 2, 3, 4 that is different from each of J1, J2 and J3. If we had included atoms expressing Sudoku relationships between cells, there would be 3 extra atoms listed in the body of the program clause, expressing that Y1, Y2 and Y3 are Sudoku related to X. In predicate logic, we would also need 6 more atoms expressing that J1, J2 and J3 are all different from each other and different from I. But we're not going there. Coming back to example 1, you might want to print out a copy of the puzzle to consult as we proceed. Stage 1 for this example will generate 4 program clauses. Take the first 3 facts in the list. B is 1, G is 2 and L is 4. Then we look up the table to find a cell which is Sudoku related to each of B, G and L. There is only one such cell, D, and the value remaining after excluding 1, 2 and 4 is 3. So we get the program clause. The value of D is 3 if the value of B is 1, the value of G is 2, and the value of L is 4. And continuing, each time taking a subset of 3 out of the 4 initial facts, so we end up with 4 ways of doing this, ignoring reordering. Here is our example at the end of stage 1, with the heads of the new clauses shown in blue. Proceeding to stage 2 of the algorithm, let theta 2 be the set of cells whose value is determinable after stage 1, and let sigma 2 be the set of cells whose value is not yet determinable from the PROLOG program clauses written so far. Now, for each of the cells X in sigma 2, we will again search for 3 cells, Y1, Y2 and Y3, with 3 distinct values, J1, J2 and J3 respectively, with all 3 of these cells Sudoku related to X. And then write down the corresponding PROLOG clause where I is the value from the set 1, 2, 3, 4 that is different from each of J1, J2 and J3. Stage 2 for our running example starts with 8 cells in theta 2, whose value is determinable, and will generate 8 program clauses, such as those shown. These clauses are not the only ones possible. For example, we could have had A is 2, an alternative to this one, if B is 1, E is 4 and M is 3. The algorithm requires that we just need one such clause for each cell in sigma 2. At the end of stage 2, we have all the cells with their values determinable from the PROLOG program. The final cleanup stage is to add a P if false tautology program clause for each of the other 48 cell value atoms. This allows us to query all possible values of a cell. So here is a complete listing of a PROLOG program generated by the algorithm for Sudoku example 001. And continuing. Now, you might be wondering, why don't we write one giant PROLOG program that contains all possible clauses, program clauses of this form? Well, yes, in principle, one could, but it would contain almost 500,000 program clauses. Again, some advanced advertising. Stay around for LLI 2 to see how much easier this will be in predicate logic PROLOG. Let's start afresh with a new example with new initial values. If you can, print out a copy of this puzzle to consult as we solve it. In the background, I've enlisted a colleague to run the algorithm to generate a PROLOG program file, Sudoku example 002.pl, and then loaded it into PROLOG. Here is the full welcome message from SWI PROLOG. After a quick look at the initial values, I take a half guess that D is 3 and B is 4 and place the query. Oops, false. One of them must be wrong. Closer look. All right, D must be 3. Let's check that. Good. Got that right. Okay, let's try filling out the first 2 rows. Take a stab. B is 2, C is 4, D is 3, E is 4, F is 3, and H is 1. Oops, false. Now I see E and F are the wrong way round. Should be E is 3 and F is 4. Yes, good. So the first 2 rows are sorted. Continuing. Nope, mistake with M and N. Good, that's it. The puzzle done. As shown. Now, your turn. To make sure you follow the steps of the algorithm generating the PROLOG code, go back to example 2 in its initial state and identify which pairs of clauses, A, B and C shown, can actually occur as output PROLOG from the algorithm. How did you go? The only correct answer is B, with the first clause value in K generated in stage 1 and the second clause generated in stage 2. The particular errors in each of options A and C are as shown. This brings us to the end of this project lesson using PROLOG. In the next, much anticipated lesson 6.4, we'll discover how PROLOG goes about answering queries and when PROLOG might get into a loop and not be able to give an answer.